All right, so exponential growth. Today we're going to talk about growth. Tomorrow we are going to talk about decay. If you still have cell phones out or laptops, they need to go away now, okay? All right, so we talked about our story, One Grain of Rice, and we watched our little clip to give us an intro to what we're talking about. So I want to kind of talk about some of the other applications today, and then how we can create kind of an equation to represent some of this, some of these scenarios. Okay, so we'll start with a basic example here. We have a type of bacteria, and the number of cells are going to triple in number every day. On the day we begin observation, so after no time has passed at all, the first sample that we take, we have a population of 100 cells, and we're going to make a table to show the population over 5 days. Okay, so on the initial day, 0 time has passed. Agreed? When we start the experiment, 0 time has passed, and it says we observe a population of 100 cells. Now, if we're going to triple every day, after 24 hours has passed or after 1 day has passed, how many cells do we expect to have? If it's tripling. Essay? 300. Okay. After 2 days have passed, how many cells do we expect to have? 900, thank you. Okay, 3 days? 2,700, good. Sorry. 4 days? Did you say 8,100? Times 3. So I think it should be 8,100. I think you times 2. Okay, and then on the 5th day? Or after 5 days have passed? Awesome. Okay, so we know that we're getting future values here by simply multiplying by 3 to get our new thing. All right, so we can already see that within the span of 5 days, 100 bacteria cells have grown all the way to 24,300. Now, I want to know what this looks like graphically. So this is actually kind of already mapped out for us here. We're only going to be able to fit up to, on this graph that we have, up to the 4th day. So we're going to graph from the initial observation, or day 0, all the way up to the 4th day. So at day 0, we want to think about this piece right here as if it's 900. So if that first tick is 900, day 1 is going to be pretty low down here. It's just going to be like just above 0, because that's at 100 bacteria. Or sorry, I should say day 0. And then day 1 was at 300 bacteria, so that's going to be just like a tiny bit higher. Day 2 was at 900, so that is our first tick right there on the y-axis. And then day 3 was 2,700, which is here, between 1,800 and 3,600. And then day 4 was 8,100, so that is all the way up here. So when we connect these guys and look at the growth that's happening, you'll notice that we have a graph that kind of like, these ones down at the bottom, these 3 points are pretty close together, but then once we go beyond that, it kind of shoots up to the right-hand side. And that's because, as we learned with our One Grain of Rice story, exponential growth, it starts small. We can start with maybe 1 grain of rice and then have 2 the next day and have 4. But by the time we get to the end of that, it's a huge value, right? So exponential growth starts small, but it gets really big really quickly. That's why it kind of shoots off to the right-hand side there. So that's what this looks like as a graph. Okay, I also just want to show you guys what happens with the first and second differences. And just to remind you, we calculate first and second differences. We did this back in grade 9. But we calculate these by taking the y coordinates here and doing bottom minus top, bottom minus top, bottom minus top, bottom minus top. That gives us the set of first differences, 200, 600, 1,800, and 5,400. And then to calculate the second differences, I take these values from the first differences and I do bottom minus top, bottom minus top, bottom minus top. Okay? So what do you guys notice about the values in the first differences that we got? 200, 600, 1800, 5400. You guys notice about how these numbers are progressing? Something about how they're progressing? Did you figure it out, Tamala? Yeah, they are also multiplied by 3, so they are also tripling. So these guys are tripling, and these guys are tripling. How about the values in the second difference column? 400, 1200, 3600. Also tripling. Okay, so when we have an exponential relation in our data, you'll notice that the first and second differences are doing whatever is happening with the y values. So if the y values are tripling and the relation of data is exponential, the first differences will also triple and the second differences will also triple. So with an exponential relation, so I'll say exponential relations have first and second differences. That change by the same constant multiple as the y values do. In this case, the constant multiple is times 3. Okay, so if you were just simply not given an equation or anything like that and you didn't graph it, but you found the first and second differences and you noticed that everything was changing by constant multiples, we can conclude that that set of data is what we call an exponential set of data. Okay, and again, to generate these, we just take the bottom minus the top, and that gives us our new column there. Okay, so this is all well and good, but suppose I want to know how many bacteria cells we have on day 50. Ideally, I don't want to go all the way from day 0 and multiply by 3 50 times, right? That's probably a little bit tedious. We might miscount, and then we'll get the wrong answer. So somehow there must be an easier way, right? And that easier way is if we can develop a formula, or if we have a general formula where we can plug things in, I can find the bacteria population at any day I want, okay? So when we talked about the 1 grain of rice story, we were talking about how Randy asked for a single grain of rice on the first day, and we were doubling. So when we looked to find a quick way to calculate all the days in our 1 grain of rice, we were using bases of 2 to various exponents, right? We were saying, okay, so on the 30th day, we calculated 2 to the exponent 29, and that told us what was there. So if we're tripling, can somebody guess what I'm going to use in my formula? In the 1 grain of rice story, we were doing bases of 2 to various exponents. We were doubling. So if I'm tripling, I will use 3 to various exponents, right? So 3 to some exponent x, right? Because the day is always changing. But if I try to calculate day 0 in here and I sub in x equals 0 for the day, I'm getting 3 to the 0, which gives me 1. But we actually start with more bacteria than that, right? How many bacteria do we start with? 100, and then we triple from there. So I actually need to multiply by that initial value that I have, right? So when I calculate day 0, or my initial observation, I sub in 0 for my x, and I get 100 times 1. And then on day 1, I sub in 1 for my x, and I get 100 times 3. For day 2, I sub in 2, and I get 100 times 9, and so on, right? That gives me my stuff. So this leads us to our general equation for exponential growth. So I'm going to break this down for you guys, and we're going to apply it in a question here. Okay, so formula for exponential growth, we have some A value. This is going to be our initial value. Okay, kind of like the 100 cells that we started with in our first example here. So this is going to be our initial value. Our B value is kind of like the 3 in this equation, or it's also kind of like the doubling in our 1 grain of rice story. So this is going to be what we call our growth or decay factor. Now here today we're only dealing with growth, but because I'm breaking this down for you guys, I'm also going to say decay for now. Okay, and what I'm talking about is, are we doubling? Are we tripling? Okay, it could be anything. Okay, y is going to be the future value. So if I sub things into my equation, I will get out the amount of, in our example, cells, bacteria cells that I have, or whatever, the amount that I have after a certain number of days have passed. So we call this future value. Okay, and then x is going to be anything to do with time. So you'll have multiple elements in your question that have to do with time. So x is actually going to be the total time that we're looking at. So how many cells are present after 50 days, the whole stretch of time. So total time over the time it takes for one growth or decay to happen, which we call the growth period or the decay period. So in our example above, our growth period was actually, it was tripling every day. So our growth period was 1 day in our example above. Okay, so how long does it take to grow once? That's kind of the idea. Or decay, depending on what we're talking about. But today we're talking about growth. So how many days does it take to triple once? Or in our grain of rice story, how long does it take her amount of grains of rice to double? Well, that was also 1 day. And then we were looking at a variety of time periods, right? After 30 days, after 15 days. Okay, so the elements of time in your question, those will go into your x value, and then you have to calculate from there. Okay, so we're going to do a couple examples today just to get an idea of different applications that we can use. Okay, so your brother tells you a secret, and I'm sure we've all done this before. How many people, I'm sure it wasn't you, but how many people know a person that has said to them, okay, I'm going to tell you a secret, but don't tell anyone, right? Admit it if you've done that. I know you guys have. Okay, so you see no harm. You're like, I'll tell these 2 people, but I'm going to tell them not to tell anybody. But those 2 people, they also see no harm in telling another 2 people. Sorry, my thing keeps... Okay, so your brother tells you, and then you see no harm. Sorry. You see no harm, you're going to go ahead and you're going to tell 2 people. And then those 2 people, they see no harm in telling 2 people each. So these 2 guys, they tell 2 people. And this is how gossip spreads. Okay, even if it's true, this is how things start to spread. And then these 4 people, well, they also see no harm in telling 2 people. This is also how pyramid schemes work. Okay, so I think we have an idea of what's going on here. So first your brother knows, okay? And then after the first passing of the secret, how many people total know? So your brother tells you, and then how many people know? 2 people. Now, you tell 2 friends. So after the second passing, here, how many people know? Total, 4. And after the third passing, here, how many total people know? Yep. And then, how many people know after this passing? 16. Okay, and I think we can assume the pattern continues, right? Okay, so this sequence of numbers right here is actually giving me the total number. Okay, so this is a little bit different than our grains of rice story, because in our grains of rice story, we're finding out how much she gets on each individual day. Here, with this little pattern that we just created here, we're finding out how many total people know after each passing. So after the first passing, 2 people know, and then after the second passing, total of 4 people know, and then after the third passing, a total of 8 people know. So we're actually adding it together with this pattern right here. Okay, so the reason why I did that is because the question is asking us, if this pattern of spreading continues, how many people total will know after 10 passings? So I can continue this if I want, but we have a formula that we can use, and that formula says, now that I've figured out the pattern of what's happening, I have, after no passings, so at the point where the first person knows, only one person knows. It's your brother, right? And presumably maybe the person that the secret's about. But your brother knows the secret. And then what is happening with the total amount of people that know after the passings here? What's going on to get us from 1 to 2, 2 to 4, 4 to 6? What's my growth factor? It's doubling. Okay. So the total amount of people that know is doubling. Okay? And we're talking about x in terms of number of passings. So the growth period here is just each one passing. This is the total of number of people that know. So I should be able to actually calculate this pretty quick. After 10 passings, I'm going to calculate 2 to the exponent 10. And of course, when I multiply by 1, it actually doesn't really change anything. So 2 to the 10 should give me the total number of people that know after the 10th passing. What'd you get? 1,024. That is how a whole school of people ends up finding out a secret about somebody, right? So after 10 passings, 1,024 people now know the secret. Now this is only this isn't very many. So this person sees no harm, and then this person sees no harm, and then all of a sudden, 1,000 people know, right? That's a lot when we talk about a secret being passed. Okay, so that's what we get. Is everyone good with this? I can scroll? Okay. An insect colony has a current population of 50 insects. I'm going to underline that because I think that's probably important. Current population of 50 insects. What does this have to do as far as y, a, b, and x? Which variable is this represented by? A, yep, initial population, good. So current population of 50 insects, its population doubles. What is this?
Oh,
it's 2, but what is that? We have y, x, and b left. It's the b, yep. Our b value, good. And it doubles every 3 days. Okay, so that is an important thing, 3 days. And what is the population after 12 days? Now, I'm underlining these in the same color because these, anything to do with time, like I told you earlier, helps us in the calculation of our x value. Okay, so our x value, we said, is total time over, in our case, we're dealing with growth, so it's going to be the growth period. So what is the total time that I'm looking at here? How much time do I want to know? 12 days, yep. And what is the growth period? How long does it take to double once? 3 days. Okay. It is important, guys, that these two things are the same unit of measurement. Okay? Otherwise, it's not going to work for you. Okay, so, yep. You may. So if it's weeks and days, then I'll maybe change everything to days, right? Okay, so after 12 days have passed, my population should have doubled 4 times. Now I know that we could probably take 50 and then double it 4 times and then we'll have our answer. But if I want to know how much happened, like what my population is after like 14 days, that's going to be a little bit harder because 3 goes evenly into 12, but 3 doesn't go evenly into 14, right? So that's kind of where the formula comes in, and the formula is a little bit more helpful. But in this case, it could be done either way. So we're going to plug into our formula. We have an initial population of 50 insects. We are doubling, and our x value we calculated above was 4. Now please, guys, don't be the person that multiplies 50 by 2, okay? We want to do bed mass here, right? So we do 2 to the 4 and then multiply that by 50, okay? Don't do 50 times 2 and then put that to the exponent 4 because then you're violating bed mass rules, okay? Don't ever want to violate bed mass rules. So what should we get here? Yep. Marianne. Did you guys get that? 800? Okay, just making sure. Okay, and for all of these types of questions, we have quite a few different applications. We are going to interpret our final answer with a therefore sentence. So can somebody make us a therefore sentence in terms of what we just found? Interpret that for us, essay. Great. Therefore, the population after 12 days is 800 insects. Beauty. Okay, this will be on your test. Okay, I will be expecting you to write interpretations of your final answer. It's good for us to know how to do the math. It's also good for us to know how to interpret that math, right? And to know what it is that I actually just found. So I just found that after 12 days, there'll be 800 insects. Cool. Any questions for this one? Pretty straightforward. Okay, so log. Log is stored in our calculator. It's a function that is stored in our calculator. Kind of like how we can square root, and that's a function that's in our calculator, and we can square something, and that's a function in our calculator, or we can take the sign of something, and that's in our calculator. So I want everybody to look at their calculator right now, and I want you to find your log button on your calculator. Okay, you might have to press shift to get to it, or like second to get to it or something. Did everybody find it? Okay, so it's probably like on the upper right-hand side of your calculator somewhere on the right-hand side. Okay, if you have 2 buttons, I want you to use the one that doesn't have the 2 boxes with it, okay, just the regular one. Did you find yours? Yeah. Yeah? Okay, so this function here, we're going to unpack this more in advanced functions. It's technically not taught in the grade 11 course, but I usually teach it and Mr. Jensen usually teaches it because the only way you can solve questions like this if you don't have this function is you have to guess and check. And guessing and checking, if your exponent is like a decimal, is not ideal, okay, because it's going to take you a really long time. All right, so basically we use the log function to isolate for a variable in an exponent. Okay, so I'm only going to use the log button on my calculator if my unknown or my x value is in an exponent. Otherwise, I am not using the log button, okay? Now, I think we could probably guess and check for something like this, right? So if I guess and check, I want to know 3 to what exponent gives me 27, right? So I might sub into my calculator, okay, 3 to the exponent 4, and then in my calculator I would get 81, and then I would try 3 to the exponent 3, and I would get 27. So therefore, I know by guessing and checking and subbing in a variety of exponents with bases of 3 into my calculator that x is 3. But what if it's not a whole number? That's the problem, right? So this one's pretty easy to solve if that number is a whole number. Then our guess and check works just fine. But if it doesn't, then I need something else to help me with that. And that is log. So I'm going to show you how we would solve this with log, and then you guys are going to try it on this guy down here. So 3 to the x equals 27. If I have the base and that unknown exponent already alone on one side, I will take the log. So remember, the log is a function kind of like a square root. So if I were to square root, I would also do that to the other side of the equation. So if I'm going to use the log here, I will also do it to the other side of the equation. Okay? So log is a function. And log rules, just for our purposes in this course, all you need to know about log is that I have some special log rules which we'll unpack in advanced functions. But the one rule that you guys need to know is that if I have the log of something to some exponent, like I have on the left side here, I actually get to take that exponent and move it down as a multiple. I call this parachute rule. It's also called power rule. Okay, so we parachute it down, and it becomes a multiple in front of log 3, okay? The reasoning behind this is to do with the fact that logarithms are the inverse of an exponential function, and it comes from exponent rules. So the log rules are rooted in exponent rules. That's all you need to know. Okay, so I'm going to write it as a multiple out in front. So that's, log helps us get it out of the exponent and down in front as a multiple. Now I want to get x by itself. The important thing to note as well is that when I have the log of 3, the log and the 3 are now buddies, and they have to move together. Okay, I can't move one without moving the other. So I actually have to move this whole expression, and I'm going to do that by dividing by the log of 3. Pardon? What's that? Doesn't that make log 27 what? Yep, so that stays together as well. So that's my next point, is that when I have something like the log of 27 over the log of 3, I can't just cancel out the logs because they're actual functions. So I have to take the log of 27 and I divide it by the full log of 3. So the log of 27 over the log of 3 is not equal to 27 over 3. I have to actually calculate it in my calculator. Okay? So if your calculator, when you put in log, opens a bracket for you here, you're going to want to close that before you divide by the log of 3. So can you guys tell me what we get from that? 3. We should get 3 because we guessed and checked and we got 3. So that's good. So we should get 3. And then I can always do a quick little check just to make sure I got the right thing by subbing this back into my original equation for the x here and seeing if 3 to the exponent 3 does in fact give me 27. That should tell me that I got the right answer. Okay, so I want you guys to solve for x in the next question here. I'll give you a second to do that. See if you can use log to solve for x. Okay, does someone want to take us through how they solved this one? Kaylin?
So I did log 4 and then parachute x.
Okay, and you also did log of the other side, right? Okay, and then you parachuted the x. So you had x log 4 Log 35. And then what?
Divided out log 4.
Great. So we divide out that log 4. And then you're going to sub that into your calculator. And what did you get when you calculated log 35 divided by log 4? 2.564. Beauty. Okay, so please make sure you can get that on your own calculator. Okay, if you're not 100% sure if you calculated it correctly, you are going to do a quick little check. Sorry. You're going to do a quick little check, and you're going to check to see if 4 to the exponent 2.564 is going to give you approximately 35. Now, because we rounded, it's going to be slightly off. Like when I calculate 5 or 4 to the exponent 2.564, I get 34.968887. So I think that tells us that we did it correctly. Pretty close to 35. Yeah.
Say after the 4 is the 6, you don't round up.
Yeah, we would round up. Is it 5, 6, 4, 6?
It's 5, 6, 4, yeah, 4, 6.
Let's see. Log 35 divided by log 4. Yeah, so maybe we'll just add the 6 in there. And then here we'll add it there.
Oh, just add it then?
Yeah, or you can do 2.565. Yeah. Good. Okay, so we're going to apply this. Yep. Just means like approximately. Yeah. Okay, so we're going to apply this to our second example. This is going to be the second part of our insects from above. So our above insect colony is actually full of giant, intelligent mutant insects. They plot that they can overtake the Earth when their population has reached, reached 1 billion. When will we meet our doom? Or in other words, when will the population reach 1 billion insects? Okay? Or maybe we should be asking the question, when do we need to be ready to fight off this population of insects, right? When do we need to have the heavy artillery ready? Okay, so what do we know? Well, we know from our earlier question that we started with how many insects? What was our initial population? Okay, so that's going to be the same. My growth rate is also going to be the same. They are still doubling. Okay, and they double every 3 days. So that's going to be part of my x. But now, I don't know time. I don't know the total time that it's going to take for that population to reach 1 billion, right? So I have the total time over that growth rate. It was 3 days. It took 3 days to double. My total time is my unknown in this scenario because I want to know how much time it takes for us to get to 1 billion. And my future value is 1 billion. That's 9 zeros. Okay, so let's start subbing into our formula here. So I have y with 9 zeros equals a times b to the exponent x, which is t over 3. Okay, so when you plug into a formula like this and you see an unknown in the exponent, you should automatically be thinking, I'm going to use my log button on my calculator eventually here. But first, before I do that, I need the base and the exponent to be alone on one side. So I need to get rid of this multiplication of 50. What should I do? How do I get rid of a multiplication of 50? Essay? Okay, so I'm going to divide both by 50 so that I can isolate the base and the exponent over on the right side here. I'll be left with 20 million, I believe, on the left side. Okay, now we have something kind of similar to what we were working with above. I have some number equals a base to some exponent, and in that exponent I have an unknown. Okay, that is when I get to go ahead and I get to take the log of both sides. Okay, so that's what we're going to do. And whatever I do to one side, I must also do to the other. Don't forget about that. We need to keep that equation balanced. Okay, and then my log rules tell me that I get to parachute that whole exponent down and I'm going to write it in front as a multiple. So I'm going to take this t over 3, and we're going to parachute it down in front. Okay, so I'm trying to get t by itself. We're trying to solve for the time here. So let's just start by getting rid of this log 2. This is right now t over 3 times the log of 2. And we said whenever I take the log, that log and the number are now like buddies, right? They have to move together. So if I'm multiplying by the log of 2, I think we can just go ahead and divide out that log 2 so that it cancels over on the right side. And I'll also do that on the left side here. So these are now gone. Okay, and you might be tempted to put this into your calculator right now, but I usually just wait until I have the t fully isolated, and then I enter it all into my calculator at once. If you really want, you can calculate it in your calculator, and then you can leave that number in your calculator and do whatever else you need to do after that with that number with full decimals. But I think here, we only have one extra little thing to isolate for t, which is to get rid of this division by 3. So we're going to multiply each side by 3. And I'll do that over here as well. So if I enter this into my calculator, remembering that if my calculator opens a bracket here, I want to close that bracket, but you're going to do 3 times the log of 20 million equals, and then divide that by the log of 2. You calculate, Nicole? 72.76. Very good. Okay, make sure you can get that in your own calculator. And units of measurement here? Days, yes. So if we started with a growth period in days, our growth period was 3 days, our final answer that we get out for time will also be in that same unit of measurement, which is days. So therefore, we should be ready with heavy artillery I think that's how you spell artillery. If it's not, forgive me. Oh no, I just did something wrong there. Artillery, double L. Maybe it's A-R-Y, I don't know. By at least, what do you guys think? At least day 71, but maybe to be safe, we'll say day 70.
Why are we doing day 70?
Well, if the population reaches 1 billion, they're going to overtake us. So we should be ready at least a couple days early, don't you think? So in other words, the population will reach 1 billion at 72.76 days. I'm just saying, in the context of this question, we want to be ready by day 70, right? But by day 72.76, 3/4 through day 72, we're in trouble, right? We've been overtaken by the mutant insects. Okay, little note about percentages. You're going to see percentages in your first worksheet. I think it's like a growth by 6% or something like that. So if you have growth by 1%, you are going to do 100% plus that growth percent to get the total percentage. And then you're going to switch that into a decimal to get your B value, okay? So example, if I have growth by 8%, this is actually 100% plus 8%. and it's a growth factor of 108%. 100% of what I already have, plus an additional 8% is being added to that. So when I go to do my b value here, my b value, I switch the percent into a decimal, and I will write my b value as 1.08. Okay, so that's growth. Tomorrow we're going to do decay, but I'm just going to tell you now, if it's decay by a percent, it will be 100% minus the decay percent. So growth will be plus, decay will be minus. So as an example, if I'm losing value on something, like for instance, if my car is decreasing in value by 20% every year, how much of my car's value remains every year? If I decrease by 20%, how much of my value remains? 80. Good. So 80% remains after each time here, which means I would rate my b value as a decimal of 0.8. Okay? That is the deal. Okay, so we're going to try some practice today. We've got 10 minutes, so just over 10 minutes to get started.